168, 120.
Ladies and gentlemen, good morning. Good morning. Welcome into our lecture. Let's wait for a very short while and we'll start, okay? Can you hear me? Everything is fine?
Yes, everything is fine.
Great. Okay. First of all, I must apologize. Maybe someone has noticed a wrong lecture has been uploaded to Moodle. Instead of our analytical geometry, financial mathematics got there. I will fix it very shortly after this lecture, so I will upload both actually, the old and the new one. Okay, let us start. Sharing the screen. So, you remember where we stopped last time? We were transforming a general second order curve into a canonical form. You remember? So we had general, let's say quadratic curve, quadratic or second order. Which was in our notation, you remember a11 x squared plus a12 xy plus a22 y squared plus a1x plus a2y plus a9x or y0 being equal to 0. And then what we did, in particular, we didn't like the cross term, because in our canonical equations for both actually ellipses, parabolas, and hyperbolas, there is no product xy. So if you remember, for the ellipse, we have x squared over a squared plus y squared over b squared equal to 1. For, let's say, for hyperbola, similar but minus 1, for example. or let's say x squared over a squared minus y squared b squared equals to 1, or if otherwise other way around than minus 1. For a parabola, only one square is present, so we can in general write this equation in the form, let's say, for simplicity I would put it just y equals to a times x squared. Although other notations are possible, sometimes the canonical form is 2p y equals to x squared. But obviously, if the coefficient is non-zero, then you can divide or multiply by this coefficient both sides. The coefficient at x squared for a parabola must not be 0, and therefore both notations are equivalent. So in none of them, we have a product xy. Therefore, if we have a general quadratic curve given by this equation, then you remember the first thing we want to do, we want to eliminate this xy product. To that end, we perform what? What is our way of eliminating the cross product?
Linear transformations?
Yes, what kind of transformation?
Rotation.
Rotation, yes. So to get rid of A12, perform rotation with as yet unknown angle, rotation at angle alpha. Alpha, for the moment, yet unknown. So, expressing, as usual, old coordinates y the new one, we get x is x prime cosine alpha minus y prime sine alpha. Y is x prime sine alpha plus y prime cosine alpha. And this results in a similar quadratic equation for the curve in the new coordinates. Then we get something like a11 prime x prime squared plus a12 prime x prime y prime, and obviously we want this a12 prime to be 0, plus a22 prime y prime squared plus a1 prime x prime plus a2 prime y prime plus, let me put it at a prime 0 for the moment, equals to 0. What are these coefficients? These coefficients can be obtained by, as we did it actually already, substituting the expressions for x and y into the original equation, then expanding that expression and collecting the terms with x prime, with the powers of x prime and y prime. Okay, so if we do it all, then partly we have done it last time already. We can say that a11 prime is equal to the old a11 cosine squared alpha plus a12 cosine alpha sine alpha plus a22 sine squared alpha. A12 prime equals to, in general, 2 times a22 minus a11 cosine alpha sine alpha plus a12, which was originally non-zero, because if it is 0, then there is no point in performing rotation, cosine squared alpha minus sine squared alpha. Or, as we put it last time, you remember, because 2 times cosine sine is sine of 2 alpha, therefore it is a22 minus a11 sine 2 alpha plus a12 cosine squared alpha minus sine squared alpha is cosine of 2 alpha. That kind of expression. Similarly, a22 prime, the new coefficient at y prime squared, is, you can easily compute it for yourself. It is a11 sine squared alpha minus, here was a plus, but here in a22 prime it is a minus, minus a12 cosine alpha sine alpha plus a22, as you can easily guess, cosine squared alpha. Now, for the sake of completeness, let us see how the linear terms are transformed. So for a 1 prime, we get, for a1 prime, we get it is simply a1 cosine alpha plus a2 sine alpha, very similar to the formulas for the rotation. A2 prime is minus a1 sine alpha plus a2 cosine alpha. And because we applied a homogeneous linear transform to x and y, so after we expanded this expression, we got powers of xy with different coefficients. Then can you tell me please, so what is going to be a prime 0? A prime 0 is unaffected. It is same as the original a0. Unchanged. So these are in general formulas for the new coefficients of our quadratic form of our second order equation after an arbitrary rotation of coordinates. Okay, and as we did, because we want to eliminate a12 prime, so now we select alpha in such a way that a2 prime, a12 prime is 0. Assuming that a12 is not 0, because otherwise there was no point in performing the rotation in the first place, then we can say a22 minus a11 sine to alpha equals to minus a12 cosine to alpha, and dividing both sides actually by minus a12 and by in that case sine to alpha, we get a11 minus a22 over a12 equals to cotangent of 2 alpha. I think that's exactly what we obtained last time, and for this reason 2 alpha is arc cotangent of a11 minus a22 divided by a12. So what can we do? Okay, so we got this 2 alpha as our cotangent, or we got this expression for cotangent of 2 alpha. This allows us to determine alpha. But in order to compute all other coefficients, for example, a11 prime and so on, we also need expressions such as cosine squared alpha, sine squared alpha, things like that. Okay? So how would we do it? Actually, it is relatively easy. So for example, here and in other places, there is a product of cosine alpha sine alpha. But cosine alpha sine alpha is just 1/2 of sine to alpha. Okay? Or even there are possibly other ways of how you can do it. So, for example, you know there is a universal trigonometric substitution, which is which can be constructed in the following way. So, for example, if we denote by, let's say, u is, let's say, tangent, u is tangent alpha, then uh, sine of 2 alpha is 2 times u divided by u squared plus 1. Cosine of 2 alpha is u squared minus 1 divided by u squared plus 1. Okay. In this case, no, it does not help that much actually, because although we do have tangent of 2 alpha, but we would not get easily sine of 2 alpha and cosine of 2 alpha from that. Well, okay, and then we'll have to resort to this. So basically what we need to get, we need to get all those sine alpha, cosine alpha, and products. Okay, if we got tangent and cotangent of 2 alpha as expressions of our coefficients, then from this we need to determine sine alpha, cosine alpha, then all products, and get the coefficients. What is the easiest way of doing that? So if let's have a look. If, for example, we determine by beta this angle of 2 alpha, then alpha is beta halved. Alpha is beta halved, and what can we say? So we have tangent of beta, tangent or cotangent of beta, and we need to compute sine and cosine of beta halved using cotangent of beta. I'm just trying to see whether there is an easy algebraic way without really just computing these values to do so. So what can we do to that end? If we have, so what kind of expressions we may use? Obviously, we have sine squared beta plus cosine squared beta being 1, and therefore, obviously, dividing this by cosine squared beta, we get tangent, sorry, dividing by sine squared beta. So we get cotangent, we get 1 plus cotangent squared beta equals to 1 divided by sine squared beta. So obviously from this if we have cotangent beta, then we cotangent beta is a11 minus a22 divided by a12. Then we can easily get sine squared beta, but we need actually beta half. So we have two sine. So from this we get sine squared beta and possibly and get sine and cosine beta easily, of course. So we get sine beta, cosine beta. Okay. Now we say 2 times sine alpha cosine alpha, which is obviously sine 2 alpha, which is sine 2 beta, so sine beta, which is now known. So we have this product, obviously, sine alpha cosine alpha, and we have cosine squared alpha minus sine squared alpha, where cosine and sine squared alpha are not known yet, which is same as, for example, 2 times cosine squared alpha minus 1, which is cosine beta. So because cosine beta is known, we get cosine squared alpha from this, and therefore both actually cosine alpha and sine alpha are known. So this way we obtain cosine alpha sine alpha algebraically, having known only cotangent beta from the algebraic equations which I just wrote down. So we don't really need to compute arc cotangent and then apply let's say sine and cosine, then divided by 2, and apply sine and cosine again. We can do it simply by using this expression. So first of all, we obtain sine beta and cosine beta from cotangent, and then from this double angle equations, we obtain, having sine beta and cosine beta in the right hand side, we obtain cosine alpha and sine alpha. Okay, just algebraically without going into arc cotangent. So I stop here for a second. Are there any questions about this?
No.
No. Okay, that's how we'll do it in general. So now I assume that all these computations have been done, and we now have our coefficients for a prime, aij prime, in the new system, in the new coordinates x prime, y prime. We have eliminated the mixed term. Now a very important observation. So what we eventually got now, so a12 prime is now 0, and we have a11 prime x prime squared plus a22 prime y prime squared plus linear terms a1 prime x prime plus a2 prime y prime plus same a0 actually as before equals to 0. Then the shape of this curve is completely determined by the quadratic terms. The linear terms, we can eliminate the linear terms, by the way, to make things even more clear, but it is already obvious that the shape of the curve is driven by the quadratic terms. You can probably guess what happens. So how can we, by just looking at quadratic terms here, how can we tell whether, for example, in the generic case, we have an ellipse, a parabola, or a hyperbola?
Maybe we can find full square and
To find what?
oh, я не точно не знаю, как это на английском привести к полному квадрату.
Well, this is said to complete a square. Well,
Okay.
to complete a square. To some extent, you are right, but let's just see in general. Suppose that, first of all, suppose that the first case, A11 prime and A22 prime are non-zero. Suppose that they are both non-zero, okay? So then the question is it possible that x prime and y prime tend to infinity? So take arbitrarily large values. You see, if A11 and A22 are of same sign, A11, A22 of same sign, then it is not possible because, well, if they are both positive, then okay, assume they are both positive. If they are both negative, multiply the whole equation by -1 and we'll get both positive coefficients, okay? They are the same sign. So without loss of generality, assume they are positive. A11 is positive, A22 is positive, okay? What happened then? Suppose that x prime and y prime together tend to infinity. So we take arbitrarily large values for them. But in this case, the quadratic part will become grossly positive. You know already from mathematical analysis that a square has a larger order of magnitude as, for example, x tends to infinity, and y prime square has a large order of magnitude as y prime tends to infinity than the linear terms. So when x prime, y prime tend to infinity, we can completely disregard linear terms because they become insignificant compared to quadratic terms. Okay? Can disregard linear terms. Okay? Linear terms. Now, imagine that a11 and a22 are positive, and x prime squared, y prime squared tend to infinity. Is it possible from the equation we have? That's our equation. Is it possible that this coefficient is positive, and x prime squared, y prime squared tend to infinity? Of course not, because in the right-hand side there must be 0. As I said, linear terms are insignificant for very large x prime, y prime, and therefore we have an obvious contradiction. The left-hand side tends to infinity, the right-hand side is 0. So we get contradiction. Left-hand side tends to infinity, right-hand side is 0, which means it is not possible. What is not possible? That x prime, y prime both tend to infinity. Take arbitrarily large values, which means Moreover, if these coefficients are both positive, then x prime, y prime cannot be arbitrarily large by themselves. If, for example, we keep y prime constant and let x prime tend to infinity, then we get exactly the same situation. We get a hugely, an indefinitely large term a11 prime x prime squared and 0 in the left in the right hand side, which means that what this contradiction means: x prime, y prime must be bounded. They cannot tend to infinity. They, or more precisely, they cannot take arbitrarily large values. They cannot take arbitrarily large values. Okay, so what does it mean? In the new coordinates, x prime, y prime are bounded. What kind of second order curve is it that the coordinates are bounded?
Ellipse.
Ellipse.
It is an ellipse, of course. It is in general an ellipse. So basically we say ellipse or a circle. Circle is possible. Or in particular circle. But in general it is an ellipse. Okay, that's case number one. When they are non-zero and of, I would say 1.1 of same sign. Now, if they are of different sign, 1.2, they are of different sign, a prime 1 1, a prime 2 2, a prime 1 1, a prime 2 2 of different signs, but both non-zero. Then it is a hyperbola. And finally, case number two, let's say a11 is non-zero, but a22 is 0. Therefore, the equation contains only a square of x prime and not y prime squared. And therefore, really, as you have mentioned, by completing a square, we can get, in that case, we can eliminate a linear term with respect to x prime, and eliminating the linear term with respect to x prime, we see that it is a parabola, actually. Or other way around, obviously. If a11 is 0, a22 is not 0. We get a parabola. And finally, if a11 equals to a22 equals to 0, then it is not a quadratic curve. All right? It is not a quadratic curve. It is a linear equation. It is a linear equation. Okay? It is a linear equation. Also, it is possible, because we don't really know which sign, what is the sign of a prime 0 in this case. So it is possible that, for example, this ellipse in case 1 1 may degenerate, or degenerate case, or it is a degenerate case. In a degenerate case, it could be, for example, a single point or an imaginary ellipse at all, which does not correspond, does not have any degenerate cases, do not have any real points at all. So, for example, if suppose that the linear terms are a1 prime, a1, a2 prime are 0, and all other coefficients are positive. So, for example, a11 prime, a22 prime, and a0 prime are all positive. Then, obviously, for no values of x prime, y prime, won't have any way satisfying this equation. So, in this case, no points at all. It is a so-called imaginary ellipse. So, for example, single point or imaginary ellipse. So no real points at all. Okay, so also let us have a look at how we can really eliminate the linear terms here. Obviously, this is now done if we really want to eliminate them. This is done by translation. So we can also do translation of coordinates. Again, expressing old coordinates through new ones. We say x prime is a new coordinate, x double prime plus, let's say, a. Y prime equals to y double prime plus b. Then it is very easy to see what happens. This translation results in quadratic coefficients a11 prime, a22 prime being unchanged. So we still have a prime 1 1 now x double prime squared plus a22 prime y double prime squared plus and coefficients at x double prime and y double prime, they do change. So what do we get here? At x double prime, we get a1 prime plus, obviously, 2 times a11 prime multiplied by x double prime plus a2 prime, a double 1 prime times a, where a is our shift. Plus a12 prime plus 2 times a22 prime a22 prime times b y double prime plus for the free term we have a prime 0 plus a prime 0 plus obviously from the first one it is a11 prime a squared plus a 22 prime b squared, and this is all equal to 0. Please check, do you agree? That this is our equation after translation or shift. Translation or shift of the coordinates. Substituting this, expanding, we get same coefficients for quadratic terms, but obviously in the first term we multiplied by a11 prime, we also get now x double prime plus a squared, which is 2 times x double prime a, and therefore the extra coefficient for x double prime 2 times a multiplied by the front one a11 prime. That's what we got here. Similar for b, and an adjustment in the free term. I think that's correct. So now, if in general we want to get rid of linear terms, then we must consider the system. It's not always possible. For example, for a parabola, it is not possible to get rid of linear terms. We therefore the parameters of A and B are at our disposal, so we can do it as we wish. This immediately results in A being equal to minus A1 prime divided by 2 times A11 prime if A11 prime is not 0, and B equals to minus A2 prime over 2 times A22 if, A22 prime, if A22 prime is not 0. That's very important. So basically, if the corresponding quadratic coefficient is non-zero, then yes, we can perform a shift and eliminate the corresponding linear term. But if the quadratic coefficient is 0, then we cannot eliminate the linear term. And that precisely corresponds to the case of the parabola. There is no, for example, quadratic term, then we cannot eliminate the linear term, because the linear term is actually essential, in this case, in the equation for parabola. So for hyperbolic and elliptic cases, the linear terms can be completely eliminated. Effectively, this is the same as completing a square. So basically, finding the transform, the translation transform, as I mentioned, it is equivalent to the fact that in the new coordinates we do complete a square, and this results in quadratic only terms. And now by the signs of those quadratic only terms, we can say whether we have an ellipse or a hyperbola. In particular, if it is an ellipse with a single real point or no real points at all. Okay. Or if we have at least one, not at least one, but exactly one quadratic coefficient being equal to 0, both quadratic coefficients cannot vanish, because then it is not a quadratic curve at all. Then it is a parabola, as we have established. And now a very, very interesting thing. Returning back to our original expression, let us construct the following quantity, the following expression, which is called the discriminant of our curve. Let us denote it by D, which is similar to the discriminant of a quadratic equation, which you know from your school years, which is A12 squared minus 4 times A11, A22. Okay. And after an arbitrary rotation, which we did, remember we performed a rotation at an arbitrary angle alpha. After the rotation, let us construct a similar discriminant in the new coordinates, in the new coefficients. So now let us construct the new discriminant d prime being a12 prime squared minus 4 times a11 prime a22 prime, where all these coefficients a12 prime, a11 prime, a22 prime are given by these equations. Okay? So then by substituting their expressions via the original coefficients and sine alpha, cosine alpha, we expand this expression. And after just a very trivial algebra, I encourage you to do it yourself, we obtain that this discriminant is equal to the original one. So what we get, it is just same a12 squared minus 4 times a11, a22 equals to d. That's the result. So it does not depend on alpha. Because it does not depend on alpha, it is called the invariant, or an invariant, basically. An invariant means doesn't change, an invariant under rotation. And obviously, it is an invariant under translation as well, because translation doesn't change the quadratic coefficients at all. So obviously D is invariant under translation as well. Let us also examine a less well-known fact. Let us see whether D is invariant under, you remember when we started some standard linear transformations, we were talking about rotations, translations. What else actually did we consider in the first part of our lectures? Yet another relatively simple transformation. Do you remember? You remember there was a symmetry transform. Let us consider symmetries. For example, with respect to, let's say, OX prime axis. A symmetry with respect to OX prime, or let's say OX, mean that X remains unchanged. So X prime equals to X, but Y prime is of a different sign compared to Y. So it is minus Y, or other way around, X is X prime, Y is minus Y prime. Substituting this into our original equation, we get obviously X is unchanged, A11 X prime squared. Now, Y is minus Y prime, therefore we get minus A12 X prime Y prime. The quadratic term is same because it is a square of Y, plus A22 Y prime squared, plus linear terms are of little interest here because the discriminant is not related to them, plus linear and constant terms equal to 0. So if we now compute d prime, then obviously, what do we get in this case? It is minus a12 squared minus 4 times a11 a22 equals to, obviously same as a12 squares minus a11 a22 equals to d original. So d is invariant under symmetries as well. Short break, 5 minutes. Okay, ladies and gentlemen, we're back. So, what does this mean? Why did we compute this invariant? How would it help us? What do you think? Yeah?
I think that help us to understand that these two given curves are the same. So we can understand that one curve is linear transformation of another curve.
Well, in general, I think you are right. So basically what happens, first of all, D, this discriminant, as we'll now see, it really determines the shape of the curve. And it is the same before our transformations and after our transformations. Therefore, by computing this discriminant, we can determine the shape of our curve even without making any transformations. Just compute the discriminant, it is the same, you know already, it is the same under rotation, translation, and symmetries, and therefore, by taking the value of the discriminant, we can know from the very beginning what would be the shape of our curve. Let's have a look actually how it works. So suppose that in the final coordinates, we have an ellipse. So let's say ellipse in the final coordinates, x, I would use 2 prime in this case, x 2 prime squared over a squared plus y double prime squared over b squared equal to 1. So what is the value of our discriminant in this case? A11 is 0. Okay, therefore, sorry, A12. A11, the coefficient at x double prime squared. What is A11 in this case? Okay, A double prime 11. Let me call it that way.
1 over a squared.
1 over a squared. A22 double prime is 1 over b squared. A12 double prime is obviously 0 in this case. So the discriminant, we know that it is same always. It is 0 minus A11 double prime squared multiplied by A22 double prime squared, which is minus 1 divided by a squared b squared, and therefore it is negative. So ellipse corresponds to discriminant being negative. Parabola it is, for example, we know that one of the quadratic terms is 0, and we have a linear term. So we can say, for example, it is y equals to a times y double prime x double prime squared. Therefore, a11 double prime is a, and for the sake of the argument, we can say, well, it doesn't matter actually, here, where a is non-zero, obviously a is non-zero. A double prime 2 is a11, a12 double prime, they are both 0. So the discriminant is 0 minus the product of quadratic coefficients is also 0 because one of them is 0 and another one is a. 0 minus 0, which is 0. So parabola corresponds to the discriminant being equal to 0. Okay? Now, hyperbola. Hyperbola corresponds to, you can probably already guess what it would take. X double prime squared, for example, over a squared minus y double prime squared over b squared equals to 1, and therefore the discriminant is again 0 minus now 1 over a squared minus 1 over b squared, by the way, 4 times, which we missed here as well, and you didn't tell me where is the coefficient 4. It doesn't change the sign, but we must remember it. So that's coefficient 4, and there is a coefficient 4 here as well, and therefore it is plus 4 over a squared b squared, which is positive. So that's the way of how we easily distinguish between the ellipse, parabola, and hyperbola by just computing the discriminant. Let us also, and this is a very powerful way because you don't need to construct the exact transformation. If you need to plot or graph your second order equation, then you do need to perform a transform, because just knowing that it is an ellipse does not really help you, for example, to determine its size, orientation of axis, and so on. Then you really need to perform all those transformations, plot the new axis with respect to the old ones, and in those new axes there will appear a simple ellipse, for example, a simple hyperbola. But just in order to determine the shape of the curve, it is sufficient to compute the discriminant. Now, you remember there was one more degenerate case. Let's see if it corresponds to anything here. For example, if you remember, for conical sections, we would have something like y being a pair of straight lines with y being equal to plus minus kx, or y squared equal to k squared x squared, okay? Or y squared minus k squared x squared being equal to 0. From the discriminant point of view, what would it correspond to? If we compute the discriminant for this one. Or other way around, I can say k squared x squared minus y squared equals to 0.
It will be
The coefficient at x is 1 over k squared. The coefficient at y is minus 1. The mixed term is x. The mixed term is x, coefficient at x, y is 0. Therefore, it is minus 4 divided by k squared times 1. So it is 4 over k squared, and it is positive. So it is, from that point of view, it corresponds to a hyperbola from the discriminant point of view. But we know it is not a hyperbola, it is a pair of straight lines.
I'm sorry, but how did it become positive?
Oh, sorry. Minus times minus 1. You are right, of course. This coefficient is minus 1. So it is positive. Minus because it is a1 squared minus the product of quadratic terms. One of them is positive and the other one is negative. So it is altogether 4 over k squared, and it is positive. So approximately it is a hyperbola. But we know it is not a hyperbola. It is a pair of straight lines. But arguably, a pair of straight lines is indeed a degenerate case of hyperbola. So you remember that for each hyperbola, we have a pair of straight lines which correspond to the asymptotes of that hyperbola. You remember? So basically what we get here, these are like asymptotes of a hyperbola. In the degenerate case, suppose that in the right-hand side of our equation, under normalization conditions, it is 1. But suppose that we perform the following transformation. So basically, we would make this coefficient in the right-hand side, instead of 1, smaller and smaller and smaller, so it tends to 0. Or this is equivalent to making, I can rewrite this equation in the following way. So multiplying both left-hand side and right-hand side by, let's say, a certain k, or even k squared, to that end, it would be x double prime squared divided by a over k squared minus y double prime squared divided by b over k squared, which is equivalent to having k squared in the numerator. This is equivalent to having k squared in the right hand side. Now let k squared tend to 0. When k squared tend to 0, this means that our right hand side tends to 0. And we indeed obtain, eventually when it becomes 0, we obtain a pair of straight lines. So indeed, a pair of straight lines can be viewed as a degenerate a degenerate case arising from the equation for a hyperbola. So a pair of straight lines is approximately the same thing as a hyperbola from this point of view, and has a similar kind of discriminant. How can we tell whether it is a pair of straight lines or a hyperbola? The difference is what we have on the right-hand side, 1 or 0, all right? Also, this would correspond to a hyperbola with infinitely large axes, infinitely large parameters a and b, let's say, but the ratio between a and b is the same for any value of k. And that's how hyperbola is transformed into a family of, into a pair of straight lines. So take a hyperbola, proportionately increase and increase the values of a and b, but keep the ratio between a and b constant. In the limit, you will have a pair of straight lines. So a pair of straight lines, limiting case of a hyperbola. So now we know a single point is a limiting case of an ellipse when the ellipse shrinks to a single point. A pair of straight lines is a limiting case of a hyperbola. A parabola is a curve on its own, although when we consider it in polar coordinates, it is an intermediate case between the ellipse and the hyperbola. For the ellipse, eccentricity is less than 1. For a parabola, it is exactly 1. For a hyperbola, it is greater than 1. And for a pair of straight lines, it is a limiting case of a hyperbola. So that's all about it. Now we really know in all cases, generic and degenerate ones, how can we transform our second order curve to a canonical form, all right? And we know how to determine the shape of this curve even without a transformation, plus minus something. So from the discriminant, you wouldn't be able to tell whether it is an ellipse, circle, a single point, or even an empty set of points, a so-called imaginary ellipse. By the way, let us summarize, actually, it will be helpful. So D is less than 0, which means generically, in the generic case, generically ellipse, degenerate cases, well, circle is possible, single point, empty set of points, so-called imaginary ellipse. Okay, now D equals to 0. Parabola. Of course, D equals to 0 would also correspond to a linear equation altogether, but that's what we do not consider. Let's say, or a first order curve. D greater than 0 corresponds to a hyperbola, generically hyperbola. Degenerate case, pair of straight lines. Okay, that's the summary. Now, in the remaining part of this lecture, we have 20 more minutes. We will start a completely new topic, which is second order surfaces in 3D. So far, we have been studying second order curves in a plane. Now, second order surfaces in 3D. As you can imagine, we had a great variety of cases, both generic and degenerate, for second order planar curves. And therefore, when we consider surfaces in 3 dimensions, then probably we're going to get a vast multiplicity, a great number of possible cases. That's indeed true, as well as for planar curves. There are some canonical forms of second order surfaces in 3D, and similar to second order curves, we will start our study of second order surfaces with some examples. And a very important class of surfaces, by far, just extremely important, are so-called rotational surfaces. So what does it mean? So that's our first point. Rotational, or surfaces of rotation. Rotational surfaces. Now, it might be more convenient for us to consider, first of all, the coordinate system instead of x, y. Let us consider a coordinate system, let's say yz. Y, z. And, well, there is also the x-axis pointing somewhere in this direction, but that will be later. In YZ, let us consider, for example, an ellipse. It is an ellipse in the YZ plane. Okay. Now, what we will do, so it is given by some equation, y squared over a squared, ellipse in OYZ, plus z squared over b squared equals to 1. Now let us start rotating this ellipse around the vertical axis, around the z-axis. So each point is now going to be rotated. So we will rotate it. And by rotating it, we obtain a three-dimensional body. So the whole area in 3D, which is swept or filled by a rotating ellipse, is our new 3D body, which is called an ellipsoid of rotation, or rotational ellipsoid. We get a rotational ellipsoid. Now the question is, how would we construct the equation for this rotational ellipsoid from our original equation of the ellipse? And the answer is very, very, very easily. So, okay, suppose that there was this point, for example, where our original ellipse intersected the y-axis, which is located at a certain distance from the origin. And from our equation, what is this distance between O and this point? Well, it corresponds to z equal to 0. Substituting z equal to 0 into our equation, we immediately see that this distance is a. When we start rotating this ellipse around the vertical axis, then this radius vector a sweeps the whole xy plane, and therefore it would intersect x with a coordinate x equal to a as well. And for any point lying in the xy plane, this would be a distance a from the origin. Similarly, for any point at a certain coordinate z, we would have some kind of maximum z, maximum y here, which is obviously a squared, okay, a times square root of 1 minus z squared over b squared, this y coordinate. And in rotation, this distance will become the radius of rotation. So if previously it was just the maximum value of y, now it becomes a constant value of a radius in xy, in the projection to xy plane. So the idea is very simple how to get the rotation. We simply replace y squared with x squared plus y squared. And this is a general way of how we could obtain the equation for a three-dimensional body obtained from a curve in YZ by rotating rotating around the Z axis. So from this we immediately get x squared plus y squared divided by a squared plus z is unchanged, z squared over b squared equals to 1. I highly encourage you to just play with these examples and see for yourself how, let's say, the OY distance would become a radius of rotation in the projection to XY plane. And for that reason, y squared could be replaced by x squared plus y squared, which is a constant radius. So in that case, we get this type of equation. This is indeed a rotational ellipsoid. And let us consider the shape of the Earth. Okay. As we have seen in our previous examples, you remember when we were considering a transformation between topocentric and geocentric coordinates. At that time, we were considering the Earth, just as, let's say, zeroth approximation. It was a sphere of some radius r. Obviously, the equation of a sphere would be x squared plus y squared plus z squared equals to r squared, or x squared over r squared plus y squared over r squared plus z squared over r squared equals to 1. That's zeroth approximation. But the first approximation, which is more accurate, first order approximation, this is zeroth order. It is quite crude actually. First order approximation the Earth is a rotational ellipsoid. Indeed, when we say what is the radius of the Earth, this question doesn't have a meaningful answer because it is not a sphere. It is much better approximated as a rotational ellipsoid, and in this case, the polar radius, for example, from the center to the pole, this one, is not equal to the equatorial radius. So let us say A is the equatorial radius, as in this picture, and B is polar radius. We need to know the values. There is a model, obviously determining the shape and the exact radii of the Earth is the problem for the science called geodesy. And now it is used with the help of space technology, satellites. The model has been improving. Initially, it was done by geodetic measurements on the Earth's surface, so-called triangulation. Now it is done by space observations. And there is a model widely used, which is called WGS-84, which is World Geodetic System. Initially, in the current form, it was created in well, there was a long sequence. So there was 1966, 1972, and eventually in the current form of 1984 standard. And then it was just it was adjusted and made more and more precise. So current standard of 2004. Initially, it was just US Department of Defense standard. Now it is a kind of international standard because the GPS system, which is used in each and every country, is again based on this standard. When you obtain your coordinates using GPS, you get all those kilometers precisely because the shape of the Earth ellipsoid and its second order approximation, which is called geoid, we're not going to talk about it, are precisely known. So, what is the equatorial radius of the Earth? 6,378 kilometers, 137 meters, but let's say in kilometers. 6,378.137. Actually, this value, 6,378, it was very well known even before any space technology, any satellite observations started to be used in geodetic measurements. So this could be obtained by Earth-based triangulation as well. So what the space technology added to us is that we now know this up to a meter. Obviously, it is quite a strange idea. How can we know actually, the equatorial radius of the Earth up to a meter? A car parked in the equator in Ecuador, would extend the equatorial radius of the Earth by 1 or 2 meters, all right? So it doesn't really matter that much, that it is 137 or maybe 38 meters, but it is still the reference ellipsoid, the reference model. Any further improvements compared to this model are considered to be just extra second order approximations related to the exact relief of the Earth, tides in the ocean, artificial landscapes, and so on. So for the reference model, it is important that it is still known up to a meter. Now, the polar radius of the Earth. Do you remember what is the difference between the equatorial and polar radius of the Earth?
Yes.
Yes, how much?
I don't know. I don't know the exact values. I thought you meant like the
About
difference.
21 kilometer. More precisely, it is 6,356 kilometers, 758 and so on meters. Actually, the standardized value is the equatorial radius and the polar radius. Oh, sorry, and the flattening. The flattening of the Earth, or also called flattening or obliquity, but let's say flattening. What do you think? What could be a reasonable measure of flattening if we know that the Earth is a rotational ellipsoid? So if it is a rotational ellipsoid, then in any cross-section by a vertical plane, it is an ellipse. So what is our measure of flattening of an ellipse? Eccentricity. You remember the term eccentricity of an ellipse. But flattening is not eccentricity. It is a much more simple thing. So flattening is simply a minus b, this difference between the polar and the equatorial and polar radius, divided by a. Or it is 1 minus b divided by a. And this value is also standardized for the Earth. It is 1 over 298.257. For you, it is sufficient probably to remember that it is 1 over 298.3, approximately. Or even just 1 over 298. But the standard value is this. So my question is, how is, please help me, how is flattening related to eccentricity? If I want to derive eccentricity from this, eccentricity of a polar cross-section of the Earth. So we draw a plane through the Earth pole, intersecting the equatorial plane at the right angle. So then we obtain an ellipse with semi-major axis being A, semi-minor axis being B. So what is the eccentricity? Okay, you remember that B is A times square root of 1 minus A squared. Okay, therefore B over A is 1 minus A squared. Therefore, 1 minus E squared. Okay, and at the same time, B over A, B over A is 1 minus flattening. B over A is simply 1 minus flattening. And
Professor, you forgot the square root. You forgot the square root.
You are right. All right, B squared over A squared, you're absolutely right. B over A, I was wondering what am I doing? You are right. B over A is 1 minus F. Therefore, B over A squared is 1 minus F squared. And at the same time, it is 1 minus E squared. From this, it followed that 1 minus E squared equals to 1 minus F squared. That's the equation, actually, which connects eccentricity and flattening. In the left-hand side, only the eccentricity is squared. In the right-hand side, 1 minus whole f is squared. Also, we can say, continuing this, that it is equal to 1 minus 2 times f plus f squared, because f squared, f is small, f squared is significantly smaller than f, we can say, or even 2f, we can say, this is equal, of course, that it is approximately equal to 1 minus 2f. And from this it follows, that 1 minus e squared is approximately equal to 1 minus 2f, and e is approximately equal to the square root of 2f. E squared, other way around. E squared is approximately equal to 2f, not the square root, of course. Oh, yes, sorry, you're right. And e approximately equal to the square root of 2f, that's right. That's what we want. The eccentricity is approximately a square root of 2f, which means that the eccentricity, what is greater in this case, eccentricity or flattening? F is less than 1. Obviously, it is a small quantity. 2 times f is, first of all, it is greater than f, but it is still smaller than 1, because f is small. Therefore, square root of 2f is what? Square root of 2f
More than 2f.
is greater than 2f. Square root of 2f is greater than 2f. And because it is greater than 2f, then it is greater than f as well. Therefore, we can say that eccentricity is greater than f. So the eccentricity of the Earth's cross-sectional ellipse is greater than obliquity. Please compute the eccentricity. That would be a very easy home assignment. Okay? So we're done for today. Thank you. If no questions, of course.
Okay, thank you.
Thank you.
Thank you.
Goodbye.
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 Bye, thanks.
Bye.
Goodbye.